Welcome to APCV 320 Computational Thinking and Doing. This week we will talk about algorithms. Lecture slides were adapted from Professor Henry Worshon, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. This lecture will come directly from Chapter 5 of Brookshire and Brylaw book, Computer Science and Overview. Before a computer can perform a task, it must be given an algorithm telling it precisely what to do. The study of algorithms is the cornerstone of computer science. In this lecture, we will cover many of the fundamental concepts of algorithms, including algorithm discovery and representation, as well as major control concepts of iteration and recursion. In so doing, we will cover a few well-known algorithms for searching and sorting. So let's begin by reviewing the concept of an algorithm. These are the sections from the chapter on algorithms from Brookshire's book, Computer Science and Overview. We will be covering all of these topics in this lecture. An algorithm is informally defined as a set of steps that define how a task is performed. Some examples are listed here, including the conjecture that even human thinking is fundamentally a set of algorithms. In this lecture, we will look closely at this fundamental concept. Informal, loosely defined concepts are acceptable and common in everyday life, but a science must be based on well-defined terminology. Consider then the formal definition of an algorithm stated in the first bullet on this slide. Note that the definition requires that the set of steps in an algorithm be ordered. This means that the steps in an algorithm must have a well-established structure in terms of the order of their execution. This does not mean, however, that the steps must be executed sequentially, start at 1 and ending at n. Some algorithms known as parallel algorithms contain more than one sequence of steps, each designed to be executed by different processors, such as in a multi-processor machine. In such cases, the overall algorithm does not process a single thread of steps that conforms to the first step, second step scenario. Instead, the algorithm's structure is that of multiple threads that branch out and reconnect as different processors perform different parts of the overall task. Other examples include algorithms executed by circuits, such as the flip-flop circuits, in which each gate performs a single step of the overall algorithm. Here the steps are ordered by cause and effect as the action of each gate propagates throughout the circuit. The definition of an algorithm also requires that an algorithm define a terminating process, which means that the execution of an algorithm must lead to an end. The origin of this requirement is in theoretical computer science, where the goal is to answer such a question as: what are the ultimate limitations of algorithms and machines? Here, computer science seeks to distinguish between problems whose answers can be obtained algorithmically and problems whose answers lie beyond the capabilities of algorithm systems. In this context, a line is drawn between processes that culminate with an answer and those that merely proceed forever without producing a result. There are, however, meaningful applications for non-terminating processes, such as maintaining an aircraft's altitude and heading in flight. Some would argue that these non-terminating applications involve the repetition of algorithms, each of which reaches an end and then automatically repeats. Others would counter that such arguments are simply attempts to cling to an overly restrictive formal definition. In any case, the result is that the term algorithm is often used informally in reference to sequences of steps that do not necessarily define terminating processes. It is important to emphasize the distinction between an algorithm and its representation, a distinction that is analogous to that between a story and a book. A story is a conceptual in nature, whereas a book is a physical representation of a story. If a book is translated into another language, it's merely the representation of the story that changes. The story itself remains the same. In the same manner, an algorithm is abstract and distinct from its representation. A single algorithm can be represented in many ways. The distinction between an algorithm and its representation presents a problem when we want to try to communicate algorithms. A common example involves the level of detail at which an algorithm must be described. Now let's clarify the distinction between two other related concepts, programs and processes. A program is a representation of an algorithm. Within the computing community, the term program usually refers to a formal representation of an algorithm within a specific computer language. A process is defined to be the activity of executing an algorithm, more specifically the activity of executing a program. The representation of an algorithm requires some form of language. From a human perspective, this might be a natural language such as English or Spanish, or perhaps a pictorial language, as I'll show in the next slide, which describes an algorithm for folding a board from a square piece of paper. Often, however, the natural nature of communication leads to misunderstandings, sometimes because the terminology used has more than one meaning. Problems also arise over misunderstandings regarding the level of detail required. Computer science approaches these problems by establishing a well-defined set of building blocks from which algorithm representations can be constructed. Such a building block is called a primitive. Assigning precise definitions to these primitives removes much of the ambiguity. Requiring algorithms to be described in terms of these primitives establishes a uniform level of detail. A collection of primitives along with a collection of rules stating how the primitives can be combined to represent more complex ideas constitutes a programming language. We will save the formal introduction of a programming language for later in favor of a less formal, more intuitive notational system known as pseudocode. In general, a pseudocode is a notational system in which ideas can be expressed informally during the algorithm development process. It can be considered to be in between natural language and programming language. As an example of an algorithm representation, here is a pictorial representation of creating an origami bird from a piece of paper. It's a complex process and it would be quite challenging to successfully fold a board solely based on the pictorial directions. Yes, a student of origami would probably have little difficulty as they might approach the problem using primitives. This slide demonstrates what might be the primitives used in origami. As we will review later, in addition to deconstructing the complexity of folding an origami board, these primitives might also be reusable in other origami creations. So again, for now, let's forego the introduction of a formal programming language in favor of a less formal, more intuitive notational system known as pseudocode. In general, a pseudocode is a notational system in which ideas can be expressed informally during the algorithm development process. There are many such pseudocode variants because there are many programming languages in existence, and pseudocode is often derived from a formally defined programming language. Thus, the pseudocode based on Pascal may look quite different than that based on Python, upon which we will base our example. One recurring semantic structure in pseudocode is the saving of a computed value. For example, if we have computed the sum of our checking and savings account balances, we may want to save the result so we can refer to it later. In such cases, we will use the form name equal expression, where name is how we will reference the results and expression describes the computation whose result is to be saved. This pseudocode structure directly follows the equivalency of Python assignment statement storing a value into a Python variable. For example, the statement remaining funds equal checking balance plus savings balance is an assignment statement that assigns the sum of checking balance and saving balance to the name remaining funds. Thus, the term remaining funds can be used in the future statements that need to refer to that sum. Having a single instance of a name reference also decreases the opportunity for error or confusion. Another recurring semantic structure is the selection of one of two possible activities depending on the validity of a condition. Example includes, if the gross domestic product has increased, buy common stocks, otherwise sell common stocks. Buy common stock if the gross domestic product has increased and sell it otherwise. Buy or sell common stock depending on whether the gross domestic product has increased or decreased, respectively. Note that the condition will always be followed immediately by a colon. The corresponding activity will be indented. If an activity consists of multiple steps, they will all be similarly indented. If there were to be an alternative activity in the case the condition was not true, we can include the concept of else in our pseudocode. The listed statements related to leap year have been rewritten to conform to the structure. If you have a brackets condition and then a colon, and then there will be an activity, else, colon, an activity, where we have used the keywords if and else to announce the different substructures within the main structure and have used colons and indentation to delineate the boundaries of these structures. Again, the condition and the else will always be followed immediately by a colon. The corresponding activity will be indented. Multiple steps of the activity will be similarly indented. By adopting this synaptic structure for our pseudocode, we acquire a uniform way in which we are going to be expressing this common semantic structure. So in this example, whereas the natural language statement, depending on whether the year is a leap year, divide the total by 366 or 365 respectively, might possess a more creative literary style, we will consistently opt for the straightforward, which is going to be if year is leap year, then the daily total will equal total divided by 366, else the daily total would be total divided by 365. Still another common semantic structure is the repeated execution of a statement or sequence of statements as long as some condition remains true. Informal examples include, as long as there are tickets to sell, continue selling tickets, or the equivalent statement, while there are tickets to sell, keep selling tickets. For such cases, we adopt the uniform pattern, while, and you have a condition, colon, and then there is an activity. So for our pseudocode, obviously that's what we adopt. A while statement checks the condition, and if it's true, performs the activity and returns to check the condition again. However, if the condition is found to be false, we move on to the next instruction following the while structure. Thus, both of the preceding statements are reduced to while tickets remain to be sold, sell a ticket. In many programming languages, indentation often enhances the readability of a program. In Python and thus in our Python-derived pseudocode, indentation is essential to the notation. For example, in the statement if bracket not training bracket and then colon, and then if bracket temperature equal hot bracket and then another colon, then you go swimming, else with a colon you play golf, else with a colon watch television. So indentation tells us that the condition of whether temperature equals hot would not even be assessed unless it's not raining. Note the use of double equal signs, equal to differentiate between the assignment, which is the equal, and the comparison, which is the equal. The question about the temperature is nested inside the if statement and is the activity to be performed if the outer if statement condition holds true. Similarly, indentation tells us that else play golf belongs to the inner if statement rather than to the outer if statement. Without indentation, play golf or watch television are somewhat ambiguous. Pseudocode is used to describe activities that can be reused across applications. Computer science has a variety of terms for such program units, including subprogram, subroutine, procedure, method, and function, each with its own variation of meaning. Python uses the term function and the keyword def to announce the title by which the pseudocode unit will be known. Begin a pseudocode function unit with a statement of the form def name, and you have two brackets, and then you have a colon, where name is the particular name of the unit. We will then follow this introductory statement with the statements that define the unit's action. When the task performed by a function is required elsewhere in our pseudocode, it can be called by name. In this example, if two functions are named process loan and reject application, then we could request their services within an if-else structure by writing if and then process loan else reject application, which would result in the execution of the function process loan if the tested condition were true, or in the execution of the reject application if the condition were false. For example, figure 5.4 is a pseudocode representation of a function called greetings that prints the message hello 3 times. If functions are to be used in different situations, they should be designed to be as generic as possible. So for this example, hard coding the phrase hello limits the reusability of this function. What if we also needed a function to say goodbye? This leads us to the concept of parameters. As another example, a function for sorting lists of names should be designed to sort any list, not a particular list. So it should be written in such a way that the list to be sorted is not specified in the function itself. Instead, the list should be referenced by a generic name within the function's representation. In our pseudocode, we adopt the convention of listing these generic names, which are called parameters, in parentheses, on the same line in which we identify the function's name. For example, a function named sort, which is designed to sort any list of names or any list of that matters, for that matter, would begin with the statement def sort, and then you have the list. Later in the representation, where a reference to the list being sorted is required, the generic name list would be used. In turn, when the sort functionality is required, we will substitute the actual list to be sorted for list in the function sort. Thus, we will write something such as sort the organization's membership list or sort the wedding guest list, depending on our needs. The development of a program consists of two activities: discovering the underlying algorithm and representing that algorithm as a program. Up to this point, we have been concerned with the issues of algorithm representation without considering the question of how algorithms are discovered in the first place. Yet algorithm discovery is usually the more challenging step in the software development process. After all, discovering an algorithm to solve a problem requires finding a method of solving that problem. Thus, to understand how algorithms are discovered is to understand the problem-solving process. The techniques of problem solving and the need to learn more about them are not unique to computer science, but rather are topics pertinent to almost any field. The close association between the process of algorithm discovery and that of general problem solving has caused computer scientists to join with those of other disciplines in the search for better problem-solving techniques. As evidence of the elusive artistic nature of problem solving, the following loosely defined problem-solving phases were presented by the mathematician G. Polya in 1945. Phase 1, understand the problem. Phase 2, devise a plan for solving the problem. Phase 3, carry out the plan. Phase 4, evaluate the solution for accuracy and for its potential as a tool for solving other problems. So this technique remains the basic principle on which many attempts to teach problem solving skills are based today. Translated into the context of program development, these phases become: Phase 1, understand the problem. Phase 2, get an idea of how an algorithmic function might solve the problem. Phase 3, formulate the algorithm and represent it as a program. Phase 4, evaluate the program for accuracy and for its potential as a tool for solving other problems. Having presented Polya's list, we should emphasize that these phases are not the steps to be followed when trying to solve a problem, but rather phases that will be completed at some point during the solution process. Another important observation is that Polya's phases are not necessarily completed in sequence. If you approach the task of solving a problem with a rigid mindset such as, now I have finished phase 1, it's time to move on to phase 2, you are less likely to be successful. However, if you become involved with the problem and ultimately solve it, you most likely can look back at what you did and realize that you performed Polya's phases, perhaps in a different or iterative order. Successful problem solvers often start formulating strategies for solving a problem, which is phase 2, before the problem itself is entirely understood, which is phase 1. Then, if these strategies fails during phases 3 and 4, the potential problem solver gains a deeper understanding of the details of the problem, and with this deeper understanding can return to form other and hopefully more successful strategies. One could argue, however, that a true understanding of a problem is not obtained until a solution has been found. The mere fact that a problem is unsolved implies a lack of understanding. To insist on a complete understanding of the problem before proposing any solutions is therefore somewhat idealistic. As an example, consider the following problem. Person A is charged with the task of determining the ages of person B's 3 children. B tells A that the product of the children's age is 36. After considering this clue, A replies that another clue is required, so B tells A the sum of the children's ages. Again, A replies that another clue is needed, so B tells A that the oldest child plays the piano. After hearing this clue, A tells B the ages of the 3 children. How old are the 3 children? At first glance, the last clue seems to be totally unrelated to the problem, yet it is apparently this clue that allows A to finally determine the ages of the children. How can this be? Let us proceed by formulating a plan of attack, and following this plan, even though we still don't fully understand the problem, our plan will be to trace the steps described by the problem statement while keeping track of the information available to person A as the story progresses. The first clue given to person A is that the product of the children's age is 36. This means that the triple representing the factor of the 3 ages is one of those listed on the left side of this slide in figure 5.5a. The next clue is the sum of the desired triple shown on the right side of this slide in figure 5.5b. We are not told what this sum is, but we are told that this information is not enough for A to isolate the correct triple. Therefore, the desired triple must be one whose sum appears at least twice. The only triples appearing in figure 5.5b with identical sum of 13 are 166 and 229. This is the information available to A at the time the last clue is given. It is at this point that we finally understand the significance of the last clue. It has nothing to do with playing the piano, rather it is the fact that there is an oldest child. This rules out the triple 166 and thus allows us to conclude that the children's ages are 2, 2, and 9. In this case, it's not until we attempt to implement our plan for solving the problem, which is phase 3, that we gain a complete understanding of the problem, which is phase 1. Had we insisted on completing phase 1 before proceeding, we would probably never have found the children's ages. Such irregularities in the problem-solving process are fundamental to the difficulties in developing systematic approaches to problem solving. Our goal now is to study some of the repetitive structures used in describing algorithmic processes. Next, we will review iterative structures in which a collection of instructions is repeated in a looping manner. We will then next introduce the technique of recursion. In the last process, we will introduce some popular algorithms, the sequential search, the binary search, and the insertion sort. Let's start by introducing the sequential search algorithm. Consider the problem of searching within a list for the occurrence of a particular target value. We want to develop an algorithm that determines whether that value is in the list. If the value is in the list, we consider the search a success, otherwise we consider it a failure. We assume that the list is sorted according to some rule for ordering its entries. Note that is specifically the condition target value is greater than test entry that assumes the list is ordered and thus allows a more efficient search. For example, if the list is the list of names, we assume the names appear in alphabetical order, or if the list consists of numeric values, we assume its entries appear in order of increasing magnitude. In our pseudocode, this process can be represented as select the first entry in the list as test entry, and then we choose the while loop where we say while target value is greater than the test entry and entries remain, then select the next entry in the list as test entry. Upon terminating this while structure, one of the two conditions will be true. Either the target value has been found or the target value is not in the list. In either case, we can detect a successful search by comparing the test entry to the target value. If they are equal, the search has been successful. Thus, we add the statement if the target value equal the test entry. If you guys remember, the equal is the comparison. Then we say, okay, declare the search a success, else declare the search a failure. To the end of the pseudocode routine. Finally, we observe that the first statement in the routine, which selects the first entry in the list as the test entry, is based on the assumption that the list in question contains at least one entry. We might reason that this is a safe guess, but just to be sure, we can position our routine as the else option of the statement. If, and then we say a list is empty, then we say, okay, declare search a failure, else, and then we can put another condition. This produces the function shown on this slide. Note that this function can be used from within other functions by using statements such as search, two brackets, the passenger list, using Daryl Baker as the target value to find out if Daryl Baker is a passenger, or search, and we put two brackets, they are empty obviously, the list of ingredients using nutmeg is the target value to find out if nutmeg appears in the list of ingredients. The control of a loop consists of the three activities: initialize, test, and modify, with each activity being required for successful loop control. The test activity causes the termination of the looping process by watching for a condition that indicates termination should take place. For example, the termination condition. It's for the purpose of this test activity that we provide a condition within each while statement of our pseudocode. In the case of the while statement, however, the condition stated is the condition under which the body of the loop should be executed. The termination condition is the negation of the condition appearing in the while structure. We should emphasize that the initialization and modification steps must lead to the appropriate termination condition. This characteristic is critical for proper loop control, and thus one should always double check for its presence when designing a loop structure. Failure to make such an evaluation can lead to errors even in the simplest cases. In a more generic context, you might hear the while loop structure referred to as a pre-test loop. Since the test for termination is performed before the body is executed, and the repeat loop structure referred to as a post-test loop, since the test for termination is performed after the body is executed. The order in which the components of loop control are executed can have subtle consequences. In fact, there are two common loop structures that differ solely in this regard. The first is exemplified by our pseudocode statement, while, and there is a condition, and then after the condition there will be an activity, whose semantics are represented in figure 5.8 in the form of a flowchart. Flowcharts use various shapes to represent individual steps and use arrows to indicate the order of the steps. The distinction between the shapes indicate the type of action involved in the associated step. A diamond indicates a decision, and a rectangle indicates an arbitrary statement or sequence of statements. Note that the test for termination in the while structure occurs before the loop's body is executed. In contrast, the structure in figure 5.9 reflects the body of the loop be executed before the test for termination is performed. In this case, the loop's body is always performed at least once, whereas in the while structure, the body is never executed if the termination condition is satisfied the first time it is tested. The insertion sort algorithm. As an additional example of using iterative structures, let us consider the problem of sorting a list of names into alphabetical order. Before proceeding, we identify a constraint to the solution, which is to sort the list within itself. In other words, we want to sort the list by shuffling its entries, as opposed to moving the list to another location. This restriction is typical in computer applications because we want to use available storage space in an efficient manner. Let us consider how we might sort the list of names Fred, Alex, Diana, Byron, Carol. The process of comparing and, as necessary, swapping names is shown from the top of this figure, row by row moving left to the right until a successfully sorted list is achieved at the bottom. Having analyzed the process of sorting a particular list, our task now is to generalize this process to discover an algorithm for sorting general lists. To this end, we observe that each row in this slide represents the same general routine. Pick up the first name in the unsorted portion of the list, slide the names greater than the extracted name down, and insert the extracted name back in the list where the new slot or pivot appears. We observe that this process should be executed repeatedly until the list is fully sorted. To begin the sorting process, the pivot should be the second entry in the list, and then before each additional execution, the pivot selection should be one entry down the list until the last entry has been positioned. In other words, as the preceding routine is repeated, the initial position of the pivot entry should advance from the second entry to the third, then to the fourth, etc., until the routine has positioned the last entry in the list. One approach to sorting this list is to note that the sublist consisting of only the top name Fred is sorted, but the sublist consisting of the top two names of Fred and Alex is not. Thus, we might pick up the card containing the name Alex, slide the name Fred down into the space where Alex was, and then place the name Alex in the slot at the top of the list as presented by the first row in figure 5.10. At this point, our list would be Alex, Fred, Diana, Byron, Carol. Now, the top two names are from a sorted sublist, but the top three do not. So we repeat the process, increasing the size of the list by one with each iteration, and we finally end with the final fully sorted list. Having identified this repetitive process and control structure, we can control the required repetition with the statements n equal to by doing the while. So we say while and the value of n does not exceed the length of list. Then we select the nth entry in list as the pivot entry. And we keep going down till we reach where it says n equal n plus 1. So where n represents the position to use for the pivot entry, and the length of list refers to the number of entries in the list. The complete pseudocode program is shown on this slide. In short, the program sorts a list by repeatedly removing an entry and inserting it into its proper place. It's because of this repeated insertion process that the underlying algorithm is called the insertion sort. Note that the structure is that of a loop within a loop, the outer loop being expressed by the first while statement and the inner loop represented by the second while statement. Each execution of the body of the outer loop results in the inner loop being initialized and executed until its termination condition is obtained. Thus, a single execution of the outer loop's body will result in several executions of the inner loop's body. The initialization component of the outer loop's control consists of establishing the initial value of n with the statement n equal to. This is needed because it doesn't make sense to start with a list of a single entry, which is always sorted. Recursive instructions provide an alternative to the loop paradigm for implementing the repetition of activities. Whereas a loop involves repeating a set of instructions such that the set of instructions is completed and then repeated, recursion involves repeating the sort of instructions as a subtask of itself. As a way of introducing recursion, let us again tackle the problem of searching to see whether a particular entry is in a sorted list, but this time we get our foot in the door by considering the procedure we follow when searching a dictionary. In this case, we do not perform a sequential page-by-page search and certainly not an entry-by-entry search. Rather, we begin by opening the directory to a page in the area where we believe the target entry is located, or perhaps we just open it an approximate halfway point. If we're lucky, we'll find the target value there, otherwise we must continue searching. But at this point, we will have narrowed our search considerably by at least approximately 50%. To search the remaining portion of the list, we could now apply the sequential search, but instead let's apply the same approach to this portion of the list we used for the whole list. That is, we select the middle entry in the remaining portion of the list as the next entry to consider. As before, if that entry is the target value, we are finished. Otherwise, we can restrict our search to an even smaller portion of the list. Let's look at an example. This approach to the searching process is summarized in figure 5.12, where we consider the task of searching the list on the left of the figure for the entry John. We first consider the middle entry, Harry. Since our target belongs after this entry, the search continues by considering the lower half of the original list. The middle of the sublist is found to be Larry. Since our target should precede Larry, we turn our attention to the first half of the current sublist. When we interrogate the middle of that secondary sublist, we find our target John and declare the search a success. In short, our strategy is to successively divide the list in question into smaller segments until the target is found or the search is narrowed to an empty segment. We need to emphasize this last point. If the target value is not in the original list, our approach to searching the list will proceed by dividing the list into smaller segments until the segment under consideration is empty. At this point, our algorithm should recognize that the search is a failure. Figure 513 is a first draft of our thoughts using our pseudocode. It directs us to begin a search by testing to see if the list is empty. If so, we are told to report that the search is a failure. Otherwise, we are told to consider the middle entry in the list. If this entry is not the target value, we are told to search either the front half or the back half of the list. Both of these possibilities require a secondary search. It would be nice to perform these searches by calling on the services of an abstract tool. In particular, our approach is to apply a function named search to carry out these secondary searches. To complete our program, therefore, we must provide such a function, but this function should perform the same task that is expressed by the pseudocode we have already written. It should first check to see if the list it is given is empty, and if it's not, it should proceed by considering the middle entry of that list. Thus, we can supply the function we need merely by identifying the current routine as being the function named search and inserting references to that function where the secondary searches are required. The result is shown on the next slide. Note that this function contains a reference to itself. If we were following this function and came to the instruction search, we would apply the same function to the smaller list that we were applying to the original one. If that search succeeded, we would return to declare our original search successful. If this secondary search failed, we would declare that our original search is a failure. To see how the function in figure 5.14 performs its task, let us follow it as it searches the list Alice, Bill, Carol, David, Evelyn, Fred, and George for the target value Bill. Our search begins by selecting David, the middle entry, as the test entry under consideration. Since the target value Bill is less than this test entry, we are instructed to apply the function search to the list of entries preceding David, that is, the list Alice, Bill, and Carol. In so doing, we create a second copy of the search function and assign it to this secondary task. We now have two copies of our search function being executed as summarized in figure 5.15. Progress in the original copy is temporarily suspended at the instruction search sublist target value. While we apply the second copy to the task of searching the list Alice, Bill, and Carol, when we complete this secondary search, we will discard the second copy of the function, report its findings to the original copy, and continue progress in the original. In this way, the second copy of the function executes as a subordinate to the original, performing the task requested by the original module and then disappearing. The secondary search selects Bill as its test entry because that is the middle entry in the list Alice, Bill, and Carol. Since this is the same as the target value, it declares its search to be a success and terminates. At this point, we have completed the secondary search as requested by the original copy of the function, so we are able to continue the execution of that original copy. Here we are told that the result of the secondary search should be reported as the result of the original search. Thus, we report that the original search has succeeded. Our process has correctly determined that Bill is a member of the list Alice, Bill, Carol, David, Evelyn, Fred, and George. Let us now consider what happens if we ask the function in figure 5.14 to search the Alice, Carol, Evelyn, Fred, and George for the entry David. This time the original copy of the function selects Evelyn as its test entry and concludes that the target value must reside in the preceding portion of the list. It therefore requests another copy of the function to search the list of entries appearing in front of Evelyn, that is the two-entry list consisting of Alice and Carol. At this stage, our situation is as represented in figure 5.16. The second copy of the function selects Carol as its current entry and concludes that the target value must lie in the latter portion of its list. It then requests a third copy of the function to search the list of names following Carol in the list Alice and Carol. This sublist is empty, so the third copy of the function has the task of searching the empty list of the target value David. Our situation at this point is represented by figure 5.17. The original copy of the function is charged with the task of searching the list Alice, Carol, Evelyn, Fred, and George, with the test entry being Evelyn. The second copy is charged with searching the list Alice and Carol, with its test entry being Carol, and the third copy is about to begin searching the empty list. Of course, being empty, the third copy of the function quickly declares its search to be a failure and terminates. The completion of the third copy's task allows the second copy to continue its task. It notes that the search it requested was unsuccessful, declares its own task to be a failure, and terminates. This report is what the original copy of the function has been waiting for, so it can now proceed. Since the search it requested failed, it declares its own search to have failed and terminates. Our routine has correctly concluded that David is not contained in the list Alice, Carol, Evelyn, Fred, and George. The binary search algorithm is similar to the sequential search in that each algorithm requests the execution of a repetitive process. However, the implementation of this repetition is significantly different. Whereas the sequential search involves a circular form of repetition, the binary search executes each stage of the repetition as a subtask of the previous stage. This technique is known as recursion. As we have seen, the illusion created by the execution of a recursive function is the existence of multiple copies of the function, each of which is called an activation of the function. These activations are created dynamically in a telescoping manner and ultimately disappear as the algorithm advances. Of those activations existing at any given time, only one is actively progressing. The others are effectively in limbo, each waiting for another activation to terminate before it can continue. Being a repetitive process, recursive systems are just as dependent on proper control as are loop structures. Just as in loop control, recursive systems are dependent on testing for a termination condition and on a design that ensures this condition will be reached. In fact, proper recursive control involves the same three ingredients: initialization, modification, and test of termination that are required in loop control. In this section, we introduce two topics that constitute important research areas within computer science. The first of these is algorithm efficiency, and the second is algorithm correctness. Even though today's machines are capable of executing millions or billions of instructions each second, efficiency remains a major concern in algorithm design. Often the choice between efficient and inefficient algorithms can make the difference between a practical solution to a problem and an impractical one. We have presented two algorithms for searching such a list: the sequential search and the binary search. Our question now is whether the choice between these two algorithms makes any difference in searching a large list comprised of n entries. We consider the sequential search first. The sequential search algorithm starts at the beginning of the list and compares the entries found to the desired target value. Not knowing anything about the source of the target value, we cannot conclude how far into the list this search must go. We can say, though, that after many searches, we expect the average depth of the searches to be halfway through the list. Some will be shorter, but others will be longer. Thus, we estimate that over a period of time, the sequential search will investigate roughly n/2 records per search. In contrast, the binary search proceeds by comparing the target value to the middle entry in the list. If this is not the desired entry, then at least the remaining search is restricted to only half of the original list. Thus, after interrogating the middle entry in the list, the binary search has at most n/2 records still to be considered. After the second inquiry, n/4, and after the third retrieval, the list in question has dropped to no more than n/8 entries. Continuing in this fashion, mathematically we see that the target record will be found after retrieving at most log2n entries from the list. So assuming a list size of 30,000 entries on average, the sequential search would require 15,000 executions, whereas the binary search would only require a maximum of 15. We conclude that the choice between the sequential search algorithm and the binary search algorithm would have a significant impact in this application. Now let's look at the efficiency of the insertion sort algorithm. The worst case scenario is that each pivot must be compared to all the preceding entries before its proper location can be found. This occurs if the original list is in reverse order. In this case, the first pivot, the second list entry, is compared to one entry. The second pivot, the third list entry, is compared to two entries, and so on. Thus, the total number of comparison when sorting a list of n entries is 1 plus 2 plus 3 plus all the way to plus n minus 1, which is equivalent to 1/2 times, we open a bracket, n2 minus n. So for this list of 5 entries, we require 1 plus 2 plus 3 plus 4, which equals 10, otherwise calculated as 1/2 times 25 minus 5, which means 1/2 times 20, which means 20 divided by 2, which makes it 10. Why do we care about the number of comparisons? Because it directly correlates to the total amount of time required to complete. Figure 5.19 shows a graph indicating how the time required to execute the insertion sort algorithm increases as the length of the list increases. The graph is based on our worst case analysis of the algorithm, where we concluded that sorting a list of length n would require at most 1/2 times n2 minus n comparisons between list entries. On the graph, we have marked several list lengths and indicated the time required in each case. Notice that as the list lengths increase by uniform increments, the time required to sort the list increases by increasingly greater amounts. Thus, the algorithm becomes less efficient as the size of the list increases. In contrast, compare the time to execute the binary search algorithm as a function of the list size. Recall that we concluded that searching a list with n entries using this algorithm would require interrogating at most log2n entries, which again gives an approximation to the amount of time required to execute the algorithm for various list sizes. Figure 5.20 shows a graph based on this analysis, on which we have again marked several list lengths of uniformly increasing size and identified the time required by the algorithm in each case. Note that the time required by the algorithm increases by decreasing increments. That is, the binary search algorithm becomes more efficient as the size of the list increases. Recall that the fourth phase in Polya's analysis of a problem solving, section 5.3, is to evaluate the solution for accuracy and for its potential as a tool for solving other problems. The significance of the first part of this phase is exemplified by the following example. A traveler with a gold chain of 7 links must stay in an isolated hotel for 7 nights. The rent each night consists of 1 link from the chain. What is the fewest number of links that must be cut so that the traveler can pay the hotel 1 link of the chain each morning without paying for lodging in advance? To solve this problem, we first realize that not every link in the chain must be cut. If we cut only the second link, we could free both the first and the second links from the other 5. Following this insight, we are led to the solution of cutting only the second, fourth, and sixth links in the chain, a process that releases each link while cutting only 3, figure 5.21. Furthermore, and fewer cuts leaves 2 links connected, so we might conclude that the correct answer to our problem is 3. Upon reconsidering the problem, we now assume the hotel can make change from the previous night's payments. Given this assumption, we make the observation that when only the third link in the chain is cut, we obtain 3 pieces of chain of lengths 1, 2, and 4, figure 5.22. With these pieces, we can proceed as follows. First morning, give the hotel the single link. Second morning, retrieve the single link and give the hotel the 2-link piece. Third morning, give the hotel the single link. Fourth morning, retrieve the 3 links held by the hotel and give the hotel the 4-link piece. Fifth morning, give the hotel the single link. Sixth morning, retrieve the single link and give the hotel the double link piece. Seventh morning, give the hotel the single link. Consequently, our first answer, which we thought was correct, is incorrect. How then can we be sure that our new solution is correct? We might argue as follows. Since a single link must be given to the hotel on the first morning, at least 1 link of the chain must be cut, and since our new solution requires only 1 cut, it must be optimal. Translated into the programming environment, this example emphasizes the distinction between a program that's believed to be correct and a program that is correct. The two are not necessarily the same. The data processing community is full of horror stories involving software that, although known to be correct, still failed at a critical moment because of some unforeseen situation. Verification of software is therefore an important undertaking, and the search for efficient verification techniques constitutes an active field of research in computer science. A major line of research in this area attempts to apply the techniques of formal logic to prove the correctness of a program. That is, the goal is to apply formal logic to prove that the algorithm represented by a program does what it is intended to do. The underlying thesis is that by reducing the verification process to a formal procedure, one is protected from the inaccurate conclusions that might be associated with intuitive arguments, as was the case in the gold chain problem. Let us consider this approach to program verification in more detail. A formal proof of a program's correctness is based on the specification under which the program was designed. In short, a proof of correctness begins with the assumption that certain conditions called preconditions are satisfied at the beginning of the program's execution. A proof of correctness proceeds by identifying statements called assertions that can be established at various points in the program. The result is a collection of assertions, each being a consequence of the program's preconditions and the sequence of instructions that led to the point in the program at which the assertion is established. If the assertion so established at the end of the program corresponds to the desired output specification, which are called postconditions, we conclude that the program is correct. So that wraps up this lecture. I know that was rather fast kind of going through it. Some of the slides you may need to review in more detail, particularly those teaser slides, and perhaps the assertion sort would require another pass through. So this concludes the lecture, and certainly you can email me questions after watching the lecture recording.